where big ideas about the universe are gently untangled and turned into calm bedtime stories about science. This space is made for listening with heavy eyes, slow breathing, and a mind that is curious but not in a hurry. If it feels comfortable, take a quiet moment to let the comments know where in the world this video is finding you and what time it is for you right now. It is always strangely soothing to see this little community stretching quietly across different countries and different time zones, all listening to the same gentle journey. If peaceful science videos like this help with winding down, pressing the like button really does help this channel drift a little further across the algorithmic sea. And if you would like more of these calm explorations, you're warmly invited to subscribe. For everyone already subscribed, thank you so much for being here again. It makes a real difference to know there are familiar listeners returning for another slow dive into the universe. If you would like to be gently nudged when the next upload appears, tapping the notifications bell will make sure the next video does not quietly slip past in the background. The hope is that this video is just interesting enough to give your thoughts something soft to rest on, but not so gripping that it insists on keeping you fully awake. And if it does keep you listening a little longer than planned, at least the extra wakefulness will be spent learning something quietly beautiful about how the universe behaves. So as the light in the room settles and the outside world slows down for the night, there is a question to keep in the back of the mind. What if the same simple rule that cools a forgotten cup of tea also shapes the fate of stars and gives time its one-way flow? Tonight's journey is about that quiet rule. Entropy is a word that often sounds harsh and complicated, as if it belongs only in heavy textbooks and late-night problem sheets. In reality, it describes something the senses have always known, that warmth spreads, that tidiness drifts toward mess, that colours blend, that ordered patterns soften, and that many things in the universe naturally lean toward states with more ways to be arranged. At its heart, entropy is a way of talking about possibility. A neatly stacked set of objects has only a few very specific arrangements that count as neat. The moment those objects are shuffled, tossed or stirred, the number of possible arrangements explodes. Most of those arrangements look messy, and only a tiny fraction look organized. The universe does not choose mess on purpose. It simply explores all the possibilities it can, and there are far more messy ones than tidy ones. There are several different lenses through which entropy can be seen, and each one tells part of the same soft story. In classical thermodynamics, entropy is tied to heat and energy, and explains why no engine can be perfectly efficient, and why heat always drifts from hotter places to cooler ones. In the statistical view, entropy is about counting how many invisible microscopic configurations hide beneath the smooth surface of what can be seen. In everyday life, entropy appears as milk swirling into coffee, as steam disappearing into the air, as ice turning slowly into water, and as a once ordered room gradually rearranging itself into creative chaos. Entropy is also at the heart of deeper puzzles. It quietly shapes the arrow of time, the feeling that yesterday is fixed, tomorrow is open, and the present is always moving forward. It governs the glow of stars, the churning of weather systems, the delicate structures of living cells, the way information is stored and erased, and even the far future of the cosmos as a whole. In this video, entropy will be followed from the scale of a single cooling drink all the way out to galaxies and black holes. The aim is not to rush toward any final conclusion, but to wander slowly through the landscapes that entropy creates, noticing the patterns that repeat themselves in different places and different forms. Along the way, ideas that can sound intimidating in a classroom will be gently rephrased, using images that are simple, physical, and easy to picture with closed eyes. By the end of the journey, entropy will hopefully feel less like a cold, abstract concept and more like a familiar background character in the story of the universe. The quiet tendency for things to spread, mix, share, and settle into the most probable arrangements they can find. So as the body softens and the breathing settles into a slower rhythm, a new question waits just ahead. If entropy is always increasing, how does the universe still manage to build stars, storms, forests, and even thinking brains out of that ever-growing sea of possibilities? In the early years of the 19th century, long before the word entropy had ever been spoken aloud, engineers and scientists found themselves facing a quiet mystery, hiding inside the steam engines that powered factories, mines, and locomotives. These machines were remarkable, transforming boiling water into motion that could pull trains and drive heavy machinery. Yet no matter how carefully they were built, they all shared a stubborn limitation. No steam engine, no matter how polished or powerful, could ever turn all of its heat into useful work. Some of the energy always slipped away as warmth that simply drifted out into the air. People could measure this loss. They could feel it in the hot metal sides of boilers and the warm gusts rising from the engines. But no one fully understood why this waste was inevitable. It seemed as though nature had quietly drawn a line, a boundary beyond which efficiency simply could not pass. That line, that limit, was the first doorway into the idea of entropy. As engineers improved their designs, they realized that even the most finely tuned engine released heat that served no purpose except to spread itself thinly into the surroundings. It was like trying to carry water in a bucket full of tiny holes. No matter how quickly the bucket was filled, some of the water always trickled away. Scientists wanted to know why. What was this subtle leak in the fabric of energy? Why did nature seem to insist on it? Into this puzzle stepped people like Sadi Carnot, who studied steam engines not just as mechanical devices, but as clues to something deeper. He noticed that heat always flowed in one direction, from a hotter place to a cooler one, never the other way around. A hot furnace would warm the air around it, but the air would never spontaneously give that warmth back to make the furnace hotter. It seemed as though warmth had a natural path, a slope it preferred to travel down, and once it reached the bottom, it could not climb back up without help. To understand this slope, scientists began to think of heat in a new way. Instead of being a kind of invisible substance, heat became something that could be measured, counted, and followed as it moved from one place to another. When heat left a burning fuel and slipped into the metal walls of an engine, something changed. When it escaped into the air, something changed again. That something was eventually given a name: entropy. Entropy was introduced as a bookkeeping tool, a gentle, structured way to track how heat moved. It described how energy gradually spread itself out, becoming less concentrated and less able to do work. If heat was tightly packed inside steam under pressure, it could push pistons and lift heavy loads. But once that heat drifted into cool air, spreading itself thinly into countless particles, its ability to do anything useful faded. It had not vanished. It had simply become shared too widely to push anything more. One way to picture this is to imagine a warm iron horseshoe fresh from the forge. The moment it leaves the fire, heat begins to flow from the horseshoe into the cooler air. The horseshoe does not pull warmth from the air to become hotter again, it only cools. The warmth slips outward, travelling from a concentrated, energetic state into one that is more evenly spread out. The same thing happens if you place your hand near a mug of a hot tea. The warmth rises toward your skin, then diffuses into the room, and eventually everything reaches a gentle equilibrium. No matter how long you watch, the tea never heats itself again. The warmth has simply found a wider home. Scientists realize that this spreading out was not a flaw. It was not inefficiency caused by sloppy engineering. It was a fundamental preference of nature. Heat would always move from places where it was dense to places where it was thin, never the other way around without external effort. Entropy became the word for this preference. It measured how far heat had drifted, how widely it had spread, and how much of it had become unavailable for doing anything more. Over time, entropy came to feel less like a strict accountant and more like a quiet guide, describing the natural direction that heat prefers to travel. When a metal rod is heated at one end, the warmth spreads gradually along its length until the whole rod settles into an even temperature. When sunlight warms the ground, the heat drifts into the surrounding air until everything balances. When you leave a warm bath, the pleasant heat slowly diffuses through the water until the bath becomes lukewarm. In each case, entropy increases as the warmth becomes shared among more and more particles. This sharing is not destructive. It does not break anything or tear anything apart. Entropy simply describes how energy rearranges itself into more relaxed, more probable states. If an engineer builds a perfect machine, entropy will still rise inside it, not because the machine is flawed, but because the universe itself gently encourages heat to spread. Even in a sealed box, warmth will drift from one side to the other until both sides feel the same. In this way, entropy became a bridge between the machines people built and the natural behavior of heat everywhere in the world. It explains why a warm stone left in cool grass gives away its warmth, why morning sunlight slowly softens the chill of night, and why an engine can roar with power only as long as it has a fresh supply of concentrated energy. Once that energy spreads out, becoming evenly shared across air, metal, and space, its ability to drive anything forward simply fades into stillness. This classical picture of entropy helped unlock some of the deepest ideas in physics. It established the understanding that energy is not lost but transformed, that heat always follows a particular path, and that there is a quiet order behind the way warmth moves. The 19th century scientists who puzzled over steam engines were unknowingly uncovering a rule that governs far more than machines. They were discovering a principle that shapes the behavior of stars, the cooling of planets, the mixing of oceans, and even the direction in which time itself appears to flow. And yet at its heart, the classical birth of entropy is simply about noticing the way heat travels. It is about watching warmth leave a furnace, a cup, a stone, or a hand, and recognizing that it always spreads outward, always settles, and never spontaneously returns. Entropy began as a way to understand the limits of machines, but it became a way to understand the limits and tendencies of nature itself. As the idea grew, it quietly transformed physics, providing a foundation for everything that followed. But the story's only beginning here, because once scientists understood how heat behaved inside engines, they began to wonder about something deeper. Why does heat have this preference at all? Why does the universe choose spreading over gathering, mixing over unmixing, settling over sharpening? What hidden patterns lie underneath these familiar behaviors? It is easy to think of disorder as something that sneaks into life when no one is paying attention, as though messiness has a personality of its own. A tidy room seems to drift toward clutter. A deck of cards that was carefully arranged a moment ago becomes a jumble after a single shuffle. A pot of paint that held two distinct colours becomes cloudy and blended after only a few slow swirls. None of these changes feel surprising. In fact, they feel natural, familiar, expected. And yet, beneath that everyday familiarity hides one of the deepest truths in nature. Disordered states vastly outnumber ordered ones. To understand why disorder rises so naturally, it helps to start with the simplest kind of tidy arrangement. Imagine a deck of playing cards laid out in perfect order. Every card is exactly where it should be, forming one very specific pattern. That ordered pattern is only one among an almost unimaginably large number of possible ways those cards could be arranged. If the deck is shuffled only once, the chance of landing on that exact pattern again is so small it's practically zero. This does not happen because the shuffle is mischievous, or because order is somehow fragile. It happens because the ordered arrangement is only one tiny point inside an enormous sea of possibilities. The moment the deck is disturbed, it is overwhelmingly likely to land somewhere in that sea. The same soft logic appears everywhere. A pair of colours sitting neatly side by side in a paint jar represents a very specific arrangement. The moment a brush swirls through them, the paint molecules rearrange themselves into countless mixed combinations. The perfectly separated state becomes just one possibility among many trillions, and the mixed state becomes the most probable destination. No matter how gently the brush moves, the colours blend. No matter how slowly the jar is tilted, the mixing begins. The tidy separation is delicately narrow. The blended state stretches wide and deep. Entropy is the quiet way of describing this imbalance. It tells us that a system with many possible states is more likely to find itself in one of the abundant, disordered arrangements than in one of the rare, highly ordered ones. The universe is not biased toward mess. It simply explores all the possibilities available to it, and the messy ones outnumber the tidy ones by such an extraordinary margin that the outcome becomes almost guaranteed. This does not only apply to objects or colours or cards, it applies to warmth itself. Picture a room made of two halves. One half is warm, the other cool. This split is a kind of order, a neat arrangement in which all the energetic molecules gather on one side while the slower, cooler ones settle on the other. But this arrangement is extremely unlikely. There are vastly more ways for the warm molecules and cool molecules to be mixed than separated. So the moment the door between the halves is opened, the air begins to blend. Warmth drifts into the cooler side, and cooler air drifts into the warmer side. In only a short time, the temperature balances, the split vanishes, and the original state becomes a memory of something improbable. Even temperature, something so intangible, follows the same quiet rule. The number of blended, balanced arrangements is far larger than the number of separated ones. So when nature is left alone, balance appears not because it is morally better or physically kinder, but because it is overwhelmingly probable. In our daily lives, this probability is easy to overlook because disorder happens quietly. A tidy space feels fragile. A single misplacement is enough to begin the unravelling. But the unravelling is not caused by chaos. It is caused by mathematics. There are simply more ways for objects to be out of place than perfectly aligned. A room with 20 objects has an enormous number of possible arrangements. Only a few of these arrangements look tidy to the human eye. The rest look scattered lived in, or gently chaotic. So unless effort is constantly supplied, the objects gradually drift from the narrow path of order into the wide plane of disorder. In a way, living with entropy feels like watching a marble roll around inside a large bowl. The marble does not settle at the edges, where the balance is delicate and requires precision. It settles at the bottom, not because it chooses that spot, but because the bottom is the broadest, most stable region. Disorder is the bottom of the bowl. Order is the thin rim at the edge. The same pattern emerges in situations far beyond rooms. If a deck of cards lies unsupervised on a table, small movements, perhaps a stray breeze or a casual hand, will likely leave it in a randomized order rather than restoring it to perfect sequence. If 2 cups of water, one warm and one cool, are poured into a single bowl, the result is always a uniform temperature. The bowl never suddenly decides to divide itself into a cold half and a warm half. Such a split would require all the faster molecules to gather in one region and all the slower ones to gather in another. That arrangement is not impossible, but it is so fantastically unlikely that it may as well be. The heart of this truth lies in counting, not counting in a strict numerical way, but counting possibilities. When a system has countless microscopic parts that can rearrange themselves freely, the number of disordered arrangements climbs to truly enormous heights. A perfectly ordered state, however beautiful it may seem, is just one pattern in an ocean of options. Even the slightest movement, a breath, a vibration, a faint shift in temperature, is enough to nudge the system into that ocean. This understanding does not strip the world of its charm. In fact, it adds a new layer of appreciation. Even moments of order become more impressive when seen through the lens of entropy. A neatly aligned shelf, a carefully prepared meal, a folded stack of clothes. Each one is a small island carved out of a vast sea of possibilities. They exist not because they are natural endpoints, but because someone has put energy into creating them. The moment that energy is no longer supplied, the system relaxes and the natural drift begins. It also becomes clear why disorder never needs encouragement. It does not grow because of negligence or laziness. It grows because there are simply far more ways to be disordered than organized. A shuffled deck is just one shuffle away from deeper randomness. A jar of paint is one swirl away from cloudiness. A room is one absent-minded placement away from feeling lived in. Disorder emerges gently, mathematically, and inevitably. This quiet inevitability is the statistical reason entropy rises. It is not a force pushing things apart. It is not a law breaking structures. It is simply the universe exploring the full range of possibilities available to it. Possibilities that lean heavily toward disorder. Once this is understood, the idea of entropy begins to feel less abstract and more like an old, familiar pattern. It appears in the way milk spreads through coffee, in the way warm fog disperses through cold air, in the way shuffled cards refuse to reassemble themselves, and in the way a once crystal-clear mixture of 2 colours settles into a uniform blend. Yet even this understanding leads naturally to the next question. If nature prefers disorder so strongly, if probability leans so heavily in that direction, why does time seem to share that very preference? Why does the flow of time mirror the rise of entropy so closely, moving always forward, never back? When disorder is seen through this lens, entropy becomes much easier to understand. It is simply the natural outcome of countless possible arrangements, most of which are disordered. The rise of entropy is not dramatic or mysterious. It is the quiet settling of things into the most probable states they can occupy, guided by the mathematics of large numbers and the gentle spread of energy and matter over time. Time is one of the strangest things to think about because it feels so familiar and so obvious, yet it behaves in a way that is surprisingly difficult to explain. Every person experiences time flowing in one direction. Mornings become afternoons, ripe fruit becomes overripe, ice melts into water, and once a plate slips from a hand and shatters on the floor, the pieces never leap back together. There is never a moment when cooled tea suddenly warms itself, or when scattered papers gather neatly into a stack without help. The world changes in ways that feel irreversible, and the mind naturally interprets these changes as proof that time itself has a direction. But the deeper scientific story is not quite as simple. The basic laws that describe the motion of particles and planets do not prefer one direction of time over the other. If a ball rolls forward on a smooth floor, the equations describing it would look just as valid written backward as though the ball rolled in reverse. Nothing in the fundamental rule says that time must move from past to future, and yet that is how it feels, consistently, unshakably. There is a before and an after, a firm sense of what has already happened and what has not yet happened. This everyday experience is deeply connected to entropy. When something happens that increases entropy, the change cannot spontaneously reverse. A shattered plate represents an enormous number of possible broken arrangements, and only a tiny handful of possible whole arrangements. Rearranging itself into one of the extremely rare whole states would require a nearly impossible coincidence of countless motions. So the plate remains broken, not because the laws of motion forbid its reassembly, but because the number of disordered broken states is vastly overwhelmingly larger than the number of ordered, unbroken ones. This imbalance gives time its unmistakable direction. The rise of entropy is quiet but persistent, and as systems drift into more probable states, the forward direction of time becomes deeply woven into experience. Once something has mixed, spread, shattered, cooled, blended, or softened, the return to the original state becomes so improbable that it effectively never occurs, and the mind interprets these one-way changes as signs that time itself is flowing forward. It is easier to picture this through simple, familiar scenes. Consider a spoonful of sugar dissolving in warm water. Within moments, the crystals fade, the water becomes evenly sweet, and the original separation between solid sugar and liquid disappears. The process feels natural and smooth, but the reverse, a perfectly uniform mixture of sugar and water separating itself into clean water and reformed crystals, never happens while someone is watching, no matter how long they wait. The forward change increases entropy. The reverse would require an improbable return to a highly ordered state. Something similar happens in a room when warm air from a heater spreads into cooler corners. The warmth drifts outward until the temperature is comfortably even. There is never a moment when the air spontaneously divides itself into a neatly separated warm half and cool half again. That reversal would require a careful arrangement of countless moving molecules. The natural direction is the one that increases entropy, and because that direction is always followed, time feels like it moves forward. Even the sound of a dropped object follows this pattern. If a glass falls onto a hard surface, the energy it carried into the fall spreads outward through vibrations, sound waves, and heat. All of those small dispersed motions represent a rise in entropy, and once the energy is spread out, there is no mechanism for those scattered vibrations to reorganize themselves into a single upward push that lifts the glass back into the air. The energy has settled into a more probable state. The rise in entropy makes the event irreversible. These examples show that the arrow of time is not written into the laws of motion themselves. It emerges from the behavior of large numbers of particles and the overwhelming probability of certain outcomes. When entropy increases, the future becomes distinct from the past. The past contains the ordered conditions from which change began. The future holds the more probable, more spread out states that the system naturally moves toward. And the present is the boundary where that shifting takes place. This also helps explain why memories form in one direction. The brain records information by creating and strengthening patterns of activity, patterns that require energy and structure. Once the information is stored, the brain has moved into a new state with higher entropy overall, because building and maintaining memory involves energy consumption and heat release. Forgetting or overwriting memories increases entropy further. The mind can only recall what has already been imprinted, not what will be imprinted later. Memories belong to the past because the physical processes that store them follow the same overarching direction. Increases in entropy. Cause and effect follow this same pattern. A cause occurs when the system is in a relatively ordered, low entropy condition with many future possibilities. An effect appears when the system transitions into a more probable, higher entropy state. That transition gives events their sequence. Strike a match, and the chemicals ignite, heat spreads, and light radiates outward. Blow out a candle, and the smoke disperses into the air. The reason these actions happen in that order, not in reverse, is because the world is moving toward more likely states. None of this relies on poetic language or dramatic storytelling. It is simply a reflection of how nature behaves. Entropy acts as the quiet background principle that shapes the directionality of experience. Every action leaves behind traces, scattered molecules, diffused heat, mixed materials that cannot spontaneously undo themselves. Those traces accumulate, marking one direction of time as the natural flow. This understanding does not need to be confusing or heavy. When looked at gently, it is a calming realization. The flow of time is the gradual settling of things into more probable states. It is the steady blending of temperatures, the quiet spreading of energy, the remixing of patterns, and the continual softening of sharp differences. Time feels like it moves forward because the world around us is always exploring more possibilities, never fewer. Every moment is unique because it carries the imprint of everything that has already spread out, rearranged, or changed. And as the world relaxes into new patterns, the next moment emerges as the natural extension of what has already unfolded. Time, in this sense, is simply entropy written across experience, a gentle movement from what was contained and ordered to what becomes shared and open. Understanding this connection makes the arrow of time feel less mysterious and much more grounded. It is not an invisible force pushing the world forward. It is the result of familiar everyday behaviors, mixing, cooling, dispersing, settling, and spreading. These processes are happening constantly in the background of every moment, quietly shaping the rhythm of life. Entropy can feel abstract when described in terms of energy spreading and microscopic states, but in daily life it appears so often and so naturally that it becomes almost impossible not to notice once the idea settles in the mind. In fact, many of the small changes people take for granted are gentle demonstrations of entropy quietly doing its work. Some are familiar comforts, some are mild annoyances, all are deeply ordinary. A simple example is the cooling of a drink. When a warm mug of tea is left alone on a table, there is never a moment when it grows hotter. It does not suddenly brighten with steam or leap back toward boiling without a source of heat. Instead, it cools patiently, minute by minute, as warmth leaves the liquid and drifts into the surrounding air. This cooling happens because the heat inside the tea is more concentrated than the heat in the room. Entropy describes the tendency for that concentration to soften. The warm molecules in the tea jostle about and pass energy to cooler molecules in the air until everything finds a comfortable balance. The tea's heat does not vanish. It simply spreads itself more thinly across a wider space. The same quiet drift appears in a block of ice placed on a kitchen counter. At first it holds its shape, solid and cold, but the warmth of the room wraps around it. Heat flows into the ice, never out of it, because heat naturally moves toward places of lower energy. As the ice absorbs this warmth, it melts. Its molecules slip from a rigid structure into a more flexible, fluid arrangement. The process looks smooth and inevitable because it is. Melting is a move toward a state with more possible arrangements for the water molecules, and entropy describes that gentle broadening of possibilities. A similar spreading happens when a scent escapes its container. A freshly peeled orange, a spritz of perfume, or the unmistakable aroma of toast drifting through a hallway all behave the same way. The scent does not collect itself neatly in one corner of a room. It wanders, fills the air, and becomes evenly distributed. This spreading out is another example of entropy increasing. The molecules that carry the scent explore countless possible paths, and the state where the smell is shared across the room is far more likely than the state where it remains confined. Entropy becomes noticeable not only in the way things change on their own, but also in the way some things stubbornly refuse to stay organized. Anyone who has tried to keep a tidy space has observed that order needs constant attention, while disorder seems perfectly capable of appearing without invitation. A neatly arranged shelf slowly gathers objects that do not belong. A clean desk collects stray papers and pens as if they have a secret meeting schedule. Clothes drift into new positions despite best intentions. Tidying requires energy and intention. Mess does not. That is not a comment on personal habits. It is simply a reflection of probability. There are vastly more ways for objects to be out of place than perfectly arranged. So without steady effort, the most probable state gradually takes over. Gentle humour can soften this realization. For example, socks emerging from a dryer seem to obey their own strange physics, one that quietly encourages them to part ways. A pair goes in, but sometimes only one returns triumphantly, while the other disappears into the great unknown. Nothing supernatural is happening. It is simply easier for things to end up in scattered, unexpected configurations than in one specific tidy arrangement. Entropy is not stealing the sock. It is just nudging the system toward one of its many more probable states. Even cooking offers examples. When stirring a pot of soup, the ingredients do not naturally separate themselves back into layers. Carrots drift through broth, spices blend, heat spreads evenly, and flavours become shared. Once mixed, these components rarely unmix themselves, even when left to sit. The blended state is vastly more probable than one in which every ingredient returns to its original location. Entropy gently ensures that the soup remains harmonious rather than stratified. A warm bath behaves in the same way. The heat diffuses through the water, smoothing out hot spots until the whole bath feels comfortably even. There is no moment when the heat snaps back into a tight pocket on one side of the tub. The evenness is more probable, so the bath settles there naturally. Even when people are not thinking about temperature, smell, mixing or tidying, entropy still appears. Consider opening a window on a cool evening. The air outside drifts inward and softens the warm interior of the room. The mixture feels natural, perhaps even refreshing. But beneath that familiar sensation is the same principle: warm and cool molecules becoming evenly shared. There are many ways for the air to blend and very few ways for it to remain separated. Entropy not only describes this blending, it explains why it feels so natural. Laundry drying on a line outdoors offers yet another example. The moisture locked inside the cloth spreads into the air, evaporating and drifting away. The initial state, water concentrated in fibers, is narrow and specific. The final state, water molecules shared across a much larger space, is much more probable. Drying is simply entropy expanding the number of possible arrangements. Entropy even shows up in the way sound behaves. A loud noise spreads out from its source, losing intensity as it moves through the air. The energy does not disappear. It is shared among more and more air molecules, each carrying a tiny fraction of the original disturbance. A loud clap becomes a soft echo, and eventually blends back into silence, because the energy has distributed itself too widely to be heard. All these examples share the same quiet truth. The universe moves towards states that can be realized in many ways. A cup of hot tea, a block of ice, a scent drifting through a room, a tidy shelf, a pot of soup, a bath, a gust of air, or a loud sound each begins in a relatively ordered, concentrated state. Over time, that order relaxes. The tea cools, the ice melts, the scent spreads, the shelf becomes cluttered, the soup blends, the bath equalizes, the warm air mixes with the cool breeze, and the sound disperses. Each transition reflects a shift toward more possible arrangements, toward states that are easier to reach, easier to maintain, and statistically far more likely. Seeing entropy in everyday life does not make the world feel chaotic or unruly. Instead, it brings a gentle sense of recognition. The same principle that shapes the cooling of tea also shapes the mixing of oceans, the drifting of weather patterns, and the glow of stars. The universe is not pushing things toward chaos. It is simply allowing energy and matter to explore more possibilities. The result is a world where warm drinks cool, scents drift, order relaxes, and everything slowly settles into comfortable, probable arrangements. Entropy, when viewed this way, becomes less of a distant scientific concept and more of a familiar companion. It is present in the small explanations for why everyday life feels the way it does, guiding changes so quietly that most people never stop to notice. And yet, once the pattern is seen, it appears everywhere. Not as something threatening or dramatic, but as something calm, predictable, and deeply woven into the rhythm of how the world naturally behaves. When entropy was first introduced through the study of steam engines, it certainly helped explain why heat flows in one direction, and why no machine can convert all of its energy into useful work. But that classical picture, useful though it is, leaves a deeper question untouched. Why does heat spread at all? Why is mixing so natural? Why is unmixing so spectacularly unlikely? To answer these questions in a gentler and more complete way, the view must shift from the large and visible to the small and numerous, from the macroscopic to the microscopic. A macroscopic description is the one most people naturally use. It focuses on the big, continuous, easy-to-see qualities of a system: the temperature of a room, the pressure inside a balloon, the color of a liquid. These descriptions are calm and comfortable because they do not require tracking every tiny detail. A warm bath is simply warm. A cold drink is simply cold. No one needs to know what each individual water molecule is doing at that moment. The microscopic description, however, looks beneath this smooth surface to the countless particles dancing within it. Every molecule carries its own little story. It has a position, a speed, a direction, and a constantly changing set of neighbours. Even something as simple as a cup of warm water involves an astonishing number of moving actors, all shifting and bouncing in ways too numerous to follow. When viewed at this microscopic level, a system is no longer described by one temperature or one colour, but by the enormous collection of tiny details that make up its structure. This is where the idea of microstates becomes helpful. A microstate is a specific arrangement of all those microscopic details. Imagine a shallow wooden bowl filled with tiny beads. Each way the beads can be arranged inside the bowl, each distribution, each cluster, each little variation is a different microstate. To the eye, the bowl might look the same from a distance, a simple collection of beads gathered in one place. But zooming in reveals countless distinct patterns that all correspond to the same overall look. A macroscopic state, by contrast, is like the general appearance of the bowl from above. It does not care exactly where every single bead is positioned. It only cares about the broad outcome. The beads are all together in the bowl is full, and the colours are mixed in a certain way. A single macroscopic state can be supported by many different microstates, and in physical systems the number of possible microstates is not just large, it is staggering, so large that the mind can barely hold the idea. Another gentle metaphor involves marbles placed into a set of drawers. A macroscopic description might say that half the marbles are in the left drawer and half are in the right. But there are countless microscopic arrangements that lead to that same result. The marbles might be scattered in a completely different pattern each time, even though the overall distribution appears identical. The macroscopic state does not care where marble number 7 or marble number 23 sits. All it cares about is the general balance between the two drawers. A third image is that of grains of sand scattered on a tray. From afar, the tray may look evenly covered, but on a microscopic level the grains could be arranged in endless combinations. They could be clustered here, spaced out there, slightly overlapping in one corner and entirely separate in another. Each microscopic configuration is different. Each is a distinct microstate, but they all correspond to the same calm, even macroscopic picture. With these metaphors in mind, the statistical meaning of entropy becomes easier to imagine. Entropy measures how many microscopic arrangements correspond to a single macroscopic state. A low entropy state has very few possible microstates. A high entropy state has a vast number of them, and because nature does not prefer one microscopic arrangement over another, all are equally possible. The system naturally drifts into states that have the most microscopic configurations supporting them, simply because those states occupy the largest volume in the space of possibilities. This statistical viewpoint explains why high entropy states dominate. Consider the earlier example of beads in a bowl. If the beads are carefully arranged in a narrow stripe across the centre, that pattern is a very low entropy arrangement. There are only a few ways to make that stripe perfectly neat, but if the beads are scattered loosely throughout the bowl, that arrangement can be achieved in a huge number of different microstates. More ways means more probability. More probability means the system naturally tends to be found there. Entropy increases because systems wander toward regions of the microscopic landscape that are vastly larger and easier to reach. It is not a force pushing them. It is not a tendency toward chaos. It is simply the mathematics of large numbers. A crowded landscape of microstates means a system has more ways to be there, so it is far more likely to end up there. This is why mixing happens so naturally. If a jar contains two colors as beads, say red and blue, neatly separated on opposite sides, that separation is extremely fragile. There are very few microstates that maintain such a clean divide. The moment the jar is shaken even slightly, the beads scatter into mixed arrangements, because those mixed arrangements outnumber the tidy ones by an overwhelming margin. You could shake the jar every day for the rest of your life, and never see the beads spontaneously unmix into their perfect halves. The number of microstates supporting that tidy state is simply too small to compete. Temperature behaves the same way. A warm side of a room and a cool side of a room represent a low entropy state with very few supporting microstates. When the two sides are allowed to interact, warm and cool molecules mix into a balanced distribution. The balanced state has vastly more microstates, which makes it overwhelmingly probable. The system does not choose this state for aesthetic reasons. It settles there because it is the broadest, deepest region in the landscape of possibilities. This statistical understanding deepens the classical story. In classical thermodynamics, entropy is tied to heat loss and inefficiency. But from a statistical point of view, entropy does not describe energy disappearing. It describes energy exploring all its possible arrangements. It explains why even the most powerful steam engine cannot convert all its heat into work. Not because the machine fails, but because the ordered distribution of energy needed for perfect efficiency is a tiny target, surrounded by a vast ocean of more probable, more disordered arrangements. The statistical view also clarifies why some processes are irreversible. It is not that reversing them violates any fundamental rule. It is simply that the number of microstates leading toward disorder vastly outnumbers the microstates leading toward order. Reassembling a broken glass is not forbidden. It is just so improbable that it would require an extraordinary coincidence of countless tiny movements lining up in a specific way. A glass shatters into a myriad of possible microstates, but only a handful of states represent the perfect original shape. The forward direction has more space to move through. The backward direction is too narrow. Understanding entropy as a measure of microscopic possibilities does not make the world feel random or unpredictable. Instead, it reveals the quiet structure behind many everyday experiences. It shows why mixing, cooling, melting, diffusing and balancing all feel so natural. These processes lead to broad macroscopic states that are supported by enormous numbers of microstates. Nature does not rush toward disorder. It simply explores the largest parts of its own landscape. This gentle statistical interpretation enriches the classical understanding of entropy by revealing the hidden world beneath familiar patterns. It shows that the rise of entropy is not a preference for chaos, but a reflection of possibility. It brings a sense of softness to the idea that order requires effort, while spreading and blending happen on their own, and it helps make sense of why systems relax into states that are stable, balanced, and widely supported. Once this microscopic picture settles into place, entropy becomes less mysterious, and more like a quiet background principle that shapes how the world evolves. It is not a rule imposed from above, It is the natural outcome of millions upon millions of microscopic interactions, each one simple on its own, but together forming the gentle statistical drift towards states that can be realized in countless ways. This shift from the visible to the invisible, from macroscopic descriptions to microscopic possibilities, is one of the most important steps in understanding entropy, not just as a concept, but as a pattern woven into the fabric of nearly everything. One of the calmest ways to understand entropy is to picture it not as a march toward disorder, but as a soft, natural smoothing out of differences. Wherever there is contrast, warm beside cool, dense beside sparse, sharp beside gentle, nature tends to blur the edges, not abruptly, not dramatically, but with a quiet patience that can be seen in almost everything. Entropy is deeply tied to this smoothing, because smoothing represents a state with far more possible microscopic arrangements than sharp contrasts ever allow. Temperature differences are perhaps the clearest example. When a warm object is placed in a cooler environment, the warmth does not remain tightly held. It leaks out calmly, molecule by molecule, drifting into the surrounding air. A cold surface, in return, quietly accepts that incoming warmth until both sides meet in the middle. The process is so familiar that it hardly feels like physics at all. A warm hand wrapped around a cold mug gradually finds the mug warming while the hand cools. A spot of sunlight on a tiled floor creates a patch of heat that slowly blends into the shadows around it. What is happening is a smoothing out of temperature differences, and entropy is the mathematical way of describing this gentle drift toward uniformity. The same idea appears when particles spread out in space. If a few drops of food colouring fall into a glass of water, they begin as thin, curling trails, but even without stirring, the colour slowly blossoms through the glass. Shapes that were once sharp soften into blurry clouds, and over time the water settles into a uniform shade. A tiny nudge here or a faint vibration there encourages the molecules to explore more and more configurations, and the blended state is vastly more probable than the tidy streaks that appeared at the beginning. This is diffusion, and it is another expression of energy and matter spreading out over time. Scents behave like this too. A freshly baked loaf of bread sitting on a counter begins with a vivid aroma concentrated near the crust. But within minutes the smell drifts across the kitchen, then into nearby rooms, becoming lighter and more even as it spreads. The scent molecules do not choose to wander, they simply follow probability. The evenly dispersed state has far more microscopic variations than the small compact cloud around the loaf. The smoothing of the scent is the natural result of particles exploring the available space. Heat, particles, aromas, colours, and even small vibrations all behave this way. Differences soften, sharp edges dilute, concentrations fade. If entropy is thought of as a kind of gentle guide, this smoothing process is the signature it leaves behind. This movement toward uniformity is called equilibrium, and it is often described as the most probable state a system can reach. That phrase can sound abstract, but in practice it is straightforward. The uniform state simply corresponds to the largest number of microscopic arrangements. Using a tactile image, imagine a large bowl filled with warm water and a single cup of cooler water gently poured into one corner. At first, there is a small crisp area where the temperature differs. The cool patch has only a few arrangements available to it. But once the waters begin to mix, the number of possible configurations explodes, and the system drifts into this broader region of possibility. Eventually, every part of the bowl settles to the same temperature. Thermal equilibrium is not a special state. It is the most spacious state. Nature tends to move towards such states because they occupy the widest stretch of the landscape of possibilities. A balanced temperature is not a goal. It is simply the most likely stopping point once many tiny interactions have taken place. The same applies to the spreading of particles in air or water. A room full of scent molecules scattered evenly has an enormous number of microstates. A localized puff of perfume near the bottle has only a handful. So, given time, the scent spreads. Another way to picture this is to imagine fog drifting across a field on a cool morning. At first, the fog begins in patches, thick in some places, thin in others. But as the minutes pass, it softens and spreads, settling into a gentle, even covering. No one patch of fog moves with urgency or purpose. The drifting is quiet and unhurried. It is simply the natural balancing of countless tiny motions. Or consider warm water merging with cooler water in a bath. When the hot tap runs, a swirl of warmth rushes through the cooler pool. At first, the difference between the hot streaks and the cooler background is distinct. But gradually, without any intervention, the warmth spreads its way outward. The water becomes comfortable everywhere, not because it is trying to achieve harmony, but because the mixed arrangement is overwhelmingly more probable than the sharply separated one. The smoothing happens on its own. Systems drift toward uniformity because uniform states allow more microscopic freedom. An even temperature can be supported by countless microstates. Molecules can move quickly here, slowly there, collide at many angles, spread in many patterns. But a sharply uneven temperature forces the system into a very narrow set of microscopic possibilities. It requires all the fast molecules to gather in one region, and all the slow molecules in another. That arrangement is so hard to maintain that the slightest interaction pushes the system towards spreading out. This is why a cup of hot chocolate left on a table cools toward the temperature of the room, never the reverse. The room taking heat from the drink is hugely more probable than the drink gathering tiny amounts of heat from every molecule of air. The room has more molecules, more randomness, and more possible redistributions. Spreading is the wide path. Concentrating is the narrow one. It is also why a metal spoon left in a pot warms itself to match the surroundings. Heat travels from the warmer soup into the cooler metal until both reach a shared temperature. The process is gentle, calm, and persistent. No matter how still the pot is, the warmth continues to glide through the spoon structure. The particles in the spoon begin moving faster as they receive energy, and the particles in the soup slow slightly as energy is shared. This balancing act reflects the underlying statistical nature of entropy. The even state has countless more microscopic arrangements supporting it. When seen through this lens, entropy does not feel like a force pushing things apart. It is a quiet expression of smoothing and sharing. Wherever the world displays a sharp difference, entropy is the tendency for that difference to blur. Wherever there is concentration, it softly spreads. Wherever there is an imbalance, it gradually equalizes. These transitions are not dramatic. They are small steps toward states that simply occupy more room in the landscape of possibility. Even the most ordinary moments demonstrate this. A cold breeze entering a warm room slowly merges into the indoor air until the temperature is neither warm nor cold, but comfortably blended. A splash of colour in a bucket of paint refuses to remain isolated, and instead flows outward until the mixture is uniform. A hot frying pan set aside to cool releases its heat into the kitchen, gradually reaching the same temperature as the surrounding air. Each of these events is a quiet smoothing of contrast and a soft rise in entropy. Understanding energy as something that spreads and settles makes entropy feel less like an abstract rule, and more like a background rhythm of nature. It offers a gentle explanation for why so many processes move in one direction. They're not guided by a desire for disorder, but by the mathematics of probability. The uniform state is the broadest plateau in the landscape of configurations, so systems naturally drift toward it. Viewed this way, entropy becomes a calming idea. It is the soft blending of warm and cool, the spreading of scent, the merging of colours, and the equalizing of temperatures. It is a smoothing process that takes the edges off sharp differences and invites the world into a quieter balance. When energy spreads, when contrasts soften, when things drift toward equilibrium, entropy is simply showing how nature explores the widest and most comfortable spaces available to it. Information feels like something delicate and weightless, almost separate from the physical world. A memory, a page in a notebook, a line typed on a screen. All of them seem like ideas sitting above the material things that hold them. But in reality, information is deeply physical. It relies on structure, stability, and energy. If the structure fades, the information fades with it. If the energy disappears, the pattern disappears too. And at the heart of this connection sits entropy, quietly linking the idea of information to the behavior of matter itself. To see this connection gently, think first about what it means to store information. A written sentence in a journal is stored because the ink on the page is arranged in a very particular pattern. Each letter has a shape. Each word has a position. The page holds meaning because the arrangement of the ink differs from the blank paper around it. The neatness and clarity of the writing represent a structured, organized state, a low entropy state. There are not many microscopic ways for the ink to sit while still forming that exact sentence. If the writing smudges or fades, the number of microscopic arrangements grows. The ink becomes blurred, spread out, or mixed into the fibers. As the structure becomes less defined, the information becomes harder to recognize. More possible microstates mean higher entropy. This is why information storage requires some level of protection and energy. A book must be kept dry. A digital device must maintain power. A memory in the brain must be supported by active neural pathways. Order must be maintained for the information to remain sharp. In this sense, storing information is like keeping a tidy arrangement in a sea of possible messy ones. It requires energy, attention, or reinforcement. Without it, the system naturally drifts towards states with more possibilities where the message becomes less distinct. A library full of neatly shelved books is a carefully maintained low-entropy place. If someone were to walk through and randomly shuffle the books, the library would still contain the same paper and ink, but much less information expressed in an accessible form. The number of microscopic ways for all books in random positions is vastly larger than the number of ways to place them in perfect order. This idea becomes even clearer when thinking about erasing information. Erasing a file on a computer or wiping a whiteboard is not a neutral act. Physically, it involves introducing disorder. When a digital device deletes data, the stored patterns that represented the file are overwritten or scrambled. The tiny physical elements inside the device that once held precise positions now occupy one of many, many possible arrangements. That shift increases entropy. Erasure is a move toward a more probable state. The same happens with written notes. If a page is torn up or crumpled, the clear arrangement of letters is replaced by a jumble of ink fragments and fibers. the structured message becomes a cloud of possibilities. Erasing information is fundamentally entropic because it takes a very specific arrangement and replaces it with one of many loosely defined ones. Memories behave in a similar way. The brain stores memories by strengthening connections between neurons, forming patterns that can be reactivated. These patterns require energy and biochemical maintenance. If the pathways fade or weaken, the details become harder to retrieve. A forgotten memory is not a mysterious disappearance. It is a return to a more uncertain, more probable state, one with many possible microstates and fewer constraints. Forgetting increases entropy. Remembering is the act of maintaining structure. There is a gentle way to picture this connection using imagery from everyday life. Imagine a tidy desk covered with neatly arranged notebooks, each containing clear handwritten pages. Now imagine a gust of wind sweeping through an open window and scattering those notebooks across the floor. The sum total of paper and ink in the room has not changed. What has changed is the information that the arrangement once conveyed. Finding a specific note becomes harder. The structure is lost. The number of possible ways the papers can lie on the floor is far larger than the number of ways they can be arranged neatly on the desk. The scattered state has higher entropy. Another soft image is that of a box filled with letters arranged in a meaningful sequence, like tiles in a word game. If the box is shaken, the letters are no longer in order. The message dissolves into a random assortment. There are vast numbers of ways for the letters to fall, and only a few ways for them to spell a meaningful phrase. The random state is thus more probable. Keeping the letters arranged requires care, intention, and energy. Leaving them alone means they settle into one of the many higher entropy configurations. This statistical perspective reveals the deep link between entropy and uncertainty. When a system is in a low entropy state, the microscopic details are more restricted. The possible microstates are fewer. That means more information is known. When a system is in a high entropy state, the microscopic details are less constrained. The number of microstates is enormous, and the exact details become harder to specify. That means less information is known, or more information is missing. Entropy can be thought of as a measure of how much microscopic detail is unavailable or unresolved. High entropy means there are many possible underlying arrangements consistent with what is seen, so there is a lot that cannot be specified. Low entropy means the arrangement is tightly constrained, and the microscopic details are more predictable. Imagine a jar filled with grains of sand. If the sand is neatly layered by colour, white on top, black in the middle, red at the bottom, the system has low entropy because the arrangement is very specific. The colours convey information about the positions of individual grains in a broad sense, but if the jar is shaken, the grains mix. The colours become blended into a cloudy mixture. The information about which grain belonged where becomes lost, and the number of possible microstates increases. The entropy rises. A layered arrangement contains more information than a mixed one. Even the simple act of shuffling notes in a notebook reflects this link. A notebook filled with organised entries lets someone open it and find what they need with ease. But if the pages are torn out and shuffled, the information becomes harder to retrieve. The order is replaced by uncertainty. And uncertainty, in the statistical sense, is one of the hallmarks of entropy. In this way, entropy is not only about heat or mixing, it is just as much about how systems store, maintain and lose structure. Every message, memory, pattern and record exists because energy holds its shape against the natural pull of spreading and blurring. When structure weakens, information becomes less accessible, because the number of microscopic states that fit the visible picture increases. Understanding entropy through the lens of information transforms it from a purely physical concept into something recognizable and almost intimate. It helps explain why organizing thoughts, remembering details, safeguarding files, or preserving books requires effort. It shows why losing information feels like watching something return to a more relaxed, more probable state. And it gives a sense of unity between mental processes and physical processes. Both depend on the same quiet balance between structure and spreading, between order and possibility. Entropy, when viewed this way, becomes a soft measure of how much detail the world still holds tightly, and how much has been given over to the wide, gentle openness of uncertainty. Life often looks like it works against entropy. A seed grows into a tree with branches arranged in repeating patterns. A caterpillar transforms into a butterfly with wings marked by careful symmetry. Cells assemble themselves into tissues, tissues into organs, and organs into living beings with astonishing structure. Even a patch of moss spreading across a stone seems to create order where none existed before. At first glance, all of this appears to contradict the natural drift towards spreading and smoothing that entropy describes. But life is not defying entropy. Life is working within it, maintaining pockets of order while increasing entropy in the surroundings. Every living system must constantly fight to keep its internal structure intact. Cells contain complicated arrangements of molecules, each performing precise tasks. The inside of a cell is not a random soup. It is a crowded, organized place where proteins fold into specific shapes, membranes separate compartments, and energy flows through tiny molecular machines. This organization does not happen for free. It is built and maintained using energy. Without a continuous input of energy, the cell would lose its structure and drift toward a more probable disordered arrangement. Plants offer a peaceful example. A leaf takes in sunlight, water, and carbon dioxide, and uses this energy to build sugars. These sugars store chemical energy, which the plant later uses to create new tissues, strengthen its stems, or grow fresh buds. Every new cell added to the plant represents a local decrease in entropy, because the molecules inside are arranged in specific patterns. But this construction is paired with an increase in entropy in the environment. The process of capturing sunlight releases heat. The chemical reactions inside the leaf produce warmth that spreads outward. The ordered structure of the plant is balanced by the energy it releases into the world. Animals behave the same way, although their energy comes from different sources. A fox, for example, eats food and breaks it down into smaller molecules. This breakdown releases energy, which the fox uses to maintain its complex internal structure. Muscles, bones, nerves, and organs are all low-entropy systems that require constant upkeep. Every moment of activity, every heartbeat, every breath is powered by chemical reactions that release heat. This release increases entropy in the surroundings even as the fox keeps its own body ordered and functional. Viewed from this angle, life is not resisting entropy. Life is borrowing energy from the environment, creating pockets of order, and then returning that energy in a more spread out, less structured form. The total entropy still rises. The local decrease is small compared to the surrounding increase. The living structure exists because energy is constantly flowing through it. This flow can be pictured gently by imagining a stream running over stones. The water shapes patterns in the sand, forming ripples and curves. These patterns appear structured and intentional but they only exist because energy is flowing continuously through the system. If the stream stopped moving, the patterns would soon be erased. Life works the same way. Its order is dynamic, maintained by a steady stream of energy. Remove the flow, and the structure fades. Cells use energy in this way with almost elegant efficiency. They build molecules like proteins and DNA, which require precise arrangements of atoms. These molecules do not assemble themselves spontaneously in the right order. They are assembled using instructions encoded in the cell's genetic material and powered by chemical energy. While the cell builds this ordered structure, it also produces heat and waste molecules that diffuse outward into the environment. The cell's small decrease in entropy is paired with a larger increase in entropy outside the cell. A whole ecosystem follows this same pattern. A forest stores energy in wood, leaves, and roots. Each tree, with its branching shape and complex internal organization, represents a local reduction in entropy, but every tree also absorbs sunlight and releases heat. Wind passing through the leaves carries warmth away. Animals moving through the undergrowth release heat as they metabolize food. Microbes breaking down fallen leaves release even more. The entire forest breathes energy in and out, building structure while raising entropy around it. A useful image is to think of sunlight as a stream of low-entropy energy arriving from the sun. The sun's light is structured, concentrated energy. Plants absorb it, use it to build sugars, and then animals and microbes spread that energy through the ecosystem. As the energy moves from sunlight to sugars to movement and finally to heat drifting into the atmosphere, entropy increases at each step. Life acts like a delicate sculptor, shaping order from the incoming stream while allowing the waste heat to spread outward. This process does not violate entropy. It depends on entropy. Without energy flowing from the environment, living systems could not maintain the order they build. Without the surrounding increase in entropy, life would quickly run out of usable energy. Life is a local organizer, not a universal one. It draws a tiny amount of energy into itself to create patterns, and it lets the rest flow outward in a more probable, more disordered form. This makes life's order feel even more remarkable because it exists in fragile balance. Every living system must constantly invest energy to maintain structure, repairing molecules, pumping ions across membranes, rebuilding tissues, copying DNA, and clearing waste. Even when sitting still, a living body is quietly at work, maintaining shapes, functions, and patterns against the natural pull towards spreading and smoothing. If the energy stops, the structure begins to relax and entropy moves in. A gentle metaphor for this comes from the way branches of a tree grow. Each branch extends outward, following a pattern influenced by sunlight, gravity, and the internal flow of nutrients. The shape of the tree looks ordered, almost mathematical. But the tree does not create that pattern out of nothing. It uses sunlight to build the structure. As energy flows through the tree, some becomes fixed in wood and leaves, while the rest escapes as warmth. The tree is a temporary shape carved into the world by energy flowing through it. Leaves offer another soft image. A leaf captures sunlight and arranges that energy into sugar molecules. In doing so, it builds ordered structures, veins, pigments, cells. But most of the sunlight's energy does not stay in the leaf. It becomes heat, radiating outward into the air. A leaf is a local organizer of energy, creating form while allowing entropy to rise overall. Even a colony of bees provides a peaceful example. Bees work together to construct honeycomb, an extraordinarily ordered structure with repeating hexagonal cells. Building this structure requires energy from nectar and honey. As the bees work, they generate heat, and that warmth diffuses out of the hive. The honeycomb becomes a pocket of low entropy supported by the higher entropy released to the surroundings. From bacteria in a tide pool to forests stretching across continents, every living system follows this rule. Life reduces entropy locally, increases it globally, and relies on the flow of energy to maintain structure. Nothing about this contradicts the natural rise of entropy. Instead, it fits perfectly within it. Seeing life through this lens brings a quiet appreciation for the delicate balance in which living things exist. The order found in living systems is temporary and must be continually renewed. Energy flows through life the way wind flows through dunes, shaping patterns that would otherwise fade. Life is not fighting entropy. It is dancing with it, carving fleeting shapes into a world that constantly leans towards spreading and smoothing. And in that dance, life reveals something quietly beautiful. Even within a universe that drifts toward more probable states, there is room for pockets of complexity, patterns, forms, and structure, each held gently in place by the energy flowing through them. Air, water, clouds, storms, breezes, and waves may seem like completely different things, but they all obey the same quiet tendencies that guide every other part of nature. At their heart, they are moving fluids carrying energy from one place to another, and because entropy describes the way energy spreads and settles, it becomes a gentle, ever-present influence on the behavior of weather and oceans. Even the most dramatic storm is, at its core, the atmosphere trying to smooth out its imbalances. To see this clearly, imagine two patches of air side by side, one warm, one cool. Warm air is made of fast-moving molecules, cool air is made of slower ones. When these two regions touch, the faster molecules naturally wander into the cooler region, and the slower ones slip into the warmer region. This exchange smooths out the difference, blending the temperatures until they become equal. Air does not remain neatly separated for long. Entropy encourages the two regions to share their energy, and the mixing happens quietly, even if no wind helps it along. On a larger scale, this blending is happening across Earth's atmosphere all the time. The sun warms the surface unevenly, the equator receives more heat than the poles, and land warms faster than water. These differences create regions of warm air and cool air sitting beside each other. The atmosphere responds by trying to spread the energy more evenly. Air rises where it is warm, sinks where it is cool, and circles around in large loops that connect distant parts of the globe. These circulations are driven by the same principle that warms your hands when you hold a mug. Heat moves from concentrated areas to wider spaces, increasing entropy as it spreads. But there are moments when the atmosphere cannot smooth things out gently. Sometimes the unevenness becomes too sharp to relax quietly. When warm, moist air gathers over warm waters and cool, dry air meets it from above, the energy contrast can grow intense. Under the right conditions, this contrast becomes a storm. Storms form because nature is trying to even out an imbalance, but the imbalance is large enough that the smoothing itself becomes dramatic. A storm is not a violation of entropy. It is a product of it. It is a mechanism for redistributing energy more widely. Inside a storm, warm, moist air rises rapidly, releasing heat as it cools and condenses into clouds. This release of heat adds more energy to the surrounding air, causing stronger uplifting motions and more mixing. It may look chaotic from the outside, but viewed through entropy, it is simply the atmosphere working efficiently to spread energy through turbulence, rain, wind, and cloud formation. Even the structure of clouds reflects this smoothing process. A cloud forms when moist air cools, and water vapor condenses into tiny droplets. At first, the droplets gather in well-defined patches, but as the air moves and mixes, the droplets spread across the sky. Wispy edges soften, flat cloud tops rise and sink, and shapes drift into new patterns with every passing minute. A cloud is a constantly changing balance between condensation and evaporation, between warm air rising and cool air descending. Each change is a small step toward a more probable, more distributed state. Clouds often appear structured, cotton-like, layered, or feathered, but these shapes remain only for as long as the energy differences that created them persist. When those differences fade, the cloud gradually dissolves. The droplets evaporate, becoming invisible water vapor again, and the structure melts into thin air. This dispersal is entropy turning a temporarily ordered pattern back into a more widespread, more probable distribution. Rain itself is another example. As droplets form inside clouds, they grow heavy enough to fall, carrying energy downward. When the raindrops reach the ground, they may splash, spread, soak into soil, or evaporate into warm air rising again. Each step redistributes energy, converting concentrated heat into more dispersed forms. The familiar cycle of evaporation, condensation, rainfall, and re-evaporation is one of Earth's most elegant smoothing mechanisms, powered by sunlight and governed by entropy. Ocean water behaves in the same way, although on wider scales and over longer times. Sunlight warms the surface of the sea, especially in the tropics. Deeper water remains cool and dense. Over time, winds push surface water away from coasts, allowing cold water from the deep to rise in its place. Currents carry warm water toward colder regions and return cooler water toward the equator. Salty water sinks beneath fresher water because it is heavier. All these movements help distribute heat, salt, and nutrients, constantly working toward a more balanced state. Ocean mixing is not random. It is driven by the same principle that guides the mixing of warm and cool air. Energy flows from concentrated places to wider areas. The ocean tries to redistribute warmth evenly, even though Earth's geography and sunlight patterns make perfect balance impossible. The gentle back and forth of tides, the slow turning of large ocean currents, and the churning of waves near the surface all contribute to this smoothing out process. If you picture a single patch of warm water drifting across the surface, it gradually spreads its heat into the surrounding cooler water. The molecules mix, and the warm patch dissolves into the larger sea. The initial contrast relaxes. The spread is calm and inevitable. Thermal equilibrium is the broadest, most probable state, and the ocean moves steadily in that direction even as winds, storms, and seasons stir its layers. Entropy even appears in the way oceans interact with the atmosphere. A warm ocean surface warms the air above it, creating humidity. That air may rise and form clouds. When the water condenses into droplets, it releases heat into the surrounding air. This released heat alters wind patterns, sometimes sparking storms, sometimes calming them. The ocean and atmosphere act as a single fluid system, exchanging energy back and forth, both guided by the same smoothing tendencies. This gentle tug toward equilibrium explains why storms fade. After a powerful storm redistributes energy, lifting warm air, cooling large regions of the atmosphere, mixing wind patterns, the contrasts that sustained it become weaker. Without those contrasts, the storm loses its fuel. It slows, softens, and eventually dissolves into calmer air. the smoothing process is complete. Entropy rises, and the atmosphere settles into a more probable state where the energy is spread more evenly. Even the largest weather systems, such as jet streams and trade winds, are shaped by differences trying to balance. They exist because Earth is heated unevenly, but they persist because the planet is rotating and covered with oceans and land masses. The constant interplay of warming, cooling, rising and sinking is how the atmosphere explores its available configurations. Large patterns may persist for months, but the underlying motion is always towards smoothing and blending. Entropy's influence on weather and oceans is not violent or dramatic. It is steady, patient, and ever-present. It shows itself in the way breezes soften heat, in the way sunsets cool the land, in the way warm currents travel across oceans, and in the way clouds appear and dissolve. It explains why storms form when contrasts are sharp, and why they fade when those contrasts ease. Seeing weather through the lens of entropy can bring a kind of quiet appreciation. The atmosphere is not chaotic, it is following probabilities. The ocean is not random, it is smoothing and sharing energy. From tiny droplets of mist to towering cyclones, from the ripple of a tide pool to the pulse of vast currents, everything flows towards states that allow more microscopic freedom. Entropy is the calm, statistical backdrop that shapes even the largest and most beautiful movements of air and water on Earth. Black holes often appear in stories as strange, frightening objects, dark pits in space that pull in everything around them. But when viewed through the lens of entropy, they become something far more interesting and far more elegant. Black holes are not just dense objects. They are among the greatest collectors of entropy in the universe, holding far more microscopic possibility than any ordinary arrangement of matter could. In fact, one of the most surprising discoveries in modern physics is that black holes possess enormous entropy, much greater than the entropy of the stars, planets, or gas clouds from which they form. To understand why, it helps to begin with the idea that a black hole is not merely a thing, but a region of space defined by a boundary. That boundary is called the event horizon. It is not a surface in the usual sense. It has no texture, no colour, no material that can be touched. Instead, it marks the point at which information becomes inaccessible to the outside universe. Anything that passes across it, light, matter, or even the path of a falling particle, cannot return. The horizon is the line beyond which the contents of the black hole are hidden. This hiddenness is the key to understanding why black holes have entropy at all. Entropy is a measure of how many microscopic arrangements a system can have while still looking the same from the outside. For everyday objects, entropy comes from the enormous number of microscopic details that are impossible to track. For black holes, those details multiply to an extraordinary degree, because everything that falls in contributes to a vast set of possibilities hidden behind the horizon. Imagine, as a soft analogy, a library whose shelves are sealed behind walls. All the books inside still exist, with all their pages and patterns of ink, but none can be opened or rearranged by anyone outside. From the outside, the library appears as a simple, opaque structure. Yet on the inside there are countless ways the books could be arranged, stacked, or scattered. Each of these arrangements is a different microstate. Even though none of these internal configurations can be observed, they still contribute to the total number of possibilities. The library's hiddenness creates a kind of entropy simply because so much information is inaccessible. A black hole works in a similar way. All the matter that falls into it carries microscopic details. Its temperature, composition, arrangement of particles, and countless other variables. When the matter crosses the event horizon, those details become unreachable to the outside world. The black hole may look simple from the outside, described by only a few large-scale features such as mass, rotation, and electric charge. But hidden behind the horizon is the record of everything that ever fell in. Even though the details can no longer influence the world outside, the number of ways they could be arranged gives the black hole an enormous number of microstates. This is why black hole entropy is so large. A small black hole already holds far more microscopic possibility than a star of the same mass. A large black hole possesses an almost unimaginable number of possible internal states. The larger the horizon, the more microscopic possibilities it can hold. This means that the entropy of a black hole does not grow with its volume, as might be expected, but with the size of its boundary, the surface area of the horizon. This idea is unusual, because most objects become more complex as their interiors grow. Black holes become more complex as their boundaries expand. One way to picture this without any technical detail is to think of the horizon as a kind of cosmic billboard, where every bit of information that enters the black hole leaves a faint imprint. The details cannot escape, but they contribute to the total number of possible ways the horizon could be configured. The more mass a black hole contains, the larger its horizon. The larger the horizon, the more microscopic possibilities there are, and the more possibilities there are, the higher the entropy. This relationship leads to a surprising conclusion. Black holes may be the most entropic objects in the universe. A single black hole can contain more entropy than an entire galaxy of stars. This does not mean black holes are chaotic or disordered inside, at least not in any ordinary sense. It simply means that the number of internal configurations hidden from the outside world is enormous. A black hole formed from a collapsing star contains not only the entropy of the star itself, but also the entropy associated with all the information that once described the star's structure. Once that information disappears behind the horizon, it contributes to the black hole's entropy. The idea that black holes carry entropy was not obvious at first. For a long time, they were thought to be simple objects defined only by a small set of large-scale properties. But when scientists studied how black holes interact with radiation, energy, and the rest of the universe, it became clear that treating them as objects with entropy led to a more consistent and complete picture of how nature behaves. The entropy of a black hole is so great that even adding a modest amount of matter can increase it dramatically. A gentle analogy helps bring this into focus. Imagine adding a cupful of water to a large lake. The water becomes part of the lake's vast set of possible configurations, but the change to the lake's overall pattern is small. Now imagine adding a cupful of water to a small bowl. The addition is noticeable and changes the system more dramatically. In a similar way, adding matter to a black hole changes its entropy by increasing the size of the horizon. The black hole makes room for the new information by expanding, and that expansion corresponds to a dramatic rise in entropy. The idea that black holes have entropy might seem to contradict their reputation as simple, almost featureless objects, but it actually reveals a more subtle beauty. Black holes show that entropy is not just about heat or mixing or disorder. It is also about the number of possible configurations hidden within a system, even if those configurations are forever inaccessible. They remind us that entropy is deeply tied to information, possibility, and the limits of what can be observed. Black holes also demonstrate the universe's preference for spreading energy outward. When matter falls into a black hole, The process of falling releases heat and light into the surrounding space. The collapsing star that forms a black hole releases enormous amounts of energy before the horizon finally seals off the interior. Even after formation, a black hole continues to interact with its surroundings, affecting nearby gas, distorting light, and shaping the structure of galaxies. Each of these interactions spreads energy, increasing entropy on a cosmic scale. Despite this, the black hole itself acts as a vast reservoir of hidden entropy, a quiet, dark region where the number of microscopic possibilities grows far beyond anything seen in ordinary matter. A black hole's interior may be unreachable, but its entropy is deeply connected to the universe outside it. The presence of such enormous hidden possibility shapes the way energy flows at the edges of the hole, the way matter collapses into it, and the way space and time respond to its gravity. When viewed this way, black holes cease to feel like cosmic hazards and become something more contemplative. They are containers of possibility. They are reminders that the universe holds far more detail than can ever be seen directly. And they show that entropy is not merely a measure of spreading energy, but a measure of how richly structured reality can be, even in the darkest corners of space. The early universe offers one of the most quietly surprising ideas in all of physics. Even though it was unimaginably hot, dense, and bursting with energy, it was also a remarkably low entropy place. That may sound contradictory at first. After all, heat usually corresponds to high entropy, and the early universe was filled with light, particles, and rapid motion. But the key lies not in the temperature itself, but in how that energy was arranged. The early cosmos was extraordinarily smooth, and in a universe where gravity is allowed to act, smoothness is one of the lowest entropy states imaginable. To picture this, imagine a vast fog of light and particles stretched evenly across space. No clusters, no stars, no galaxies, no patterns. Just an almost perfectly uniform glow in every direction. This was the universe only a short time after its beginning. The energy was distributed so evenly that any two regions looked almost identical. There were no mountains or valleys in the cosmic landscape. Nothing that stood out, nothing that could be considered structure. This smoothness gives the early universe its low entropy, because there are very few microscopic ways to arrange matter so that everything remains perfectly uniform. The easiest way to understand this is to contrast it with gravitational clumping. Gravity is a force that loves to gather things. If a region of space contains slightly more matter than its surroundings, gravity pulls in even more matter, making the region denser over time. A dense clump can grow into a star, a galaxy, or a cluster of galaxies. These clumps represent high gravitational entropy because there are many different ways matter can arrange itself inside them. But in the early universe, none of those clumps existed yet. Everything was spread out smooth and even, like a freshly rolled sheet of dough. This smoothness may look simple, but it is actually very special. It takes far more precision to keep everything evenly spread than to let some regions grow or collapse. Smoothness represents low gravitational entropy because it corresponds to a small set of possible microscopic arrangements. A lumpy universe with dense regions and empty pockets has a huge number of possible configurations. A smooth universe has very few. Another way to picture this is to imagine a perfectly calm pond just after dawn. The surface is so still that it reflects the sky like a mirror. This calmness feels simple and peaceful, but it is actually quite rare. The slightest breeze, a single fish surfacing, or a fallen leaf interrupts the calm and creates ripples. There are countless ways the surface can be disturbed, and only a few ways it can remain perfectly still. The early universe was like that calm pond, quietly special because of its improbable smoothness. As the universe expanded, its entropy began to rise. Expansion gave particles room to spread out, offering new microscopic possibilities. As the cosmos grew larger, tiny irregularities, little fluctuations in density, were able to grow under gravity. These small differences, initially almost invisible, were enough to form the seeds of future structure. Slightly denser regions attracted more matter, slowly deepening into cosmic hills, while slightly emptier regions became cosmic valleys. Over enormous stretches of time, these differences grew into galaxies, stars, and planets. This growth of structure may seem like an increase in order, but from gravity's perspective, it is actually an increase in entropy. A dense region of space can be arranged in countless microscopic ways. A smooth region has far fewer options, so as structure emerged, the gravitational entropy increased dramatically. The universe was moving from its low entropy beginning into richer, more complex states, simply by following the natural pull of gravity. Expansion also made room for radiation to spread out, softening the extreme heat of the early universe. Light that was once closely packed into a small volume now drifted across a growing cosmos. This spreading of energy increased entropy further. As space stretched, photons cooled, lengthening their wavelengths and becoming less concentrated. The universe became a more probable place, less compressed, more distributed, and more open to many possible configurations. Over time, this combination of expansion and gravity transformed the early simplicity into the elaborate cosmic structures seen today. Galaxies formed with spiral arms, bulging centers, and halo regions full of dark matter. Stars ignited within those galaxies, warming their surroundings, releasing light, and spreading energy across interstellar space. Planets formed, atmospheres developed, and chemistry flourished. These intricate arrangements arose not in spite of entropy, but because the early universe began in such an improbable, low-entropy state that there was room for complexity to grow. A gentle analogy helps make this clearer. Imagine a perfectly level field of snow stretching into the distance. At first, the surface is simple and smooth, but as the day warms and the air shifts, small changes naturally appear. A little patch melts faster than its surroundings. A tiny ridge forms where the wind skims over the surface. Over hours and days, these tiny irregularities grow into complex patterns, drifts, hollows, sculpted ridges, all shaped by the natural interplay of wind, temperature, and sunlight. The smooth field, beautiful in its simplicity, contained the potential for many intricate forms. Its low entropy beginning allowed the landscape to evolve. The early universe worked the same way. Its simplicity was not a lack of structure, but the stage on which structure could emerge. If the universe had begun in a highly clumped state, full of gravitational knots and uneven distributions, there would have been far fewer pathways to build galaxies and stars. The early smoothness opened the door to complexity. Even today, the faint afterglow of that early era can be seen in the cosmic microwave background. This soft radiation fills the universe, carrying a memory of the smooth conditions that once existed. The tiny temperature variations visible in it are like the first subtle patterns on the snow, small hints of the future galaxies and clusters that would eventually form. Understanding the early universe as a low-entropy state brings a sense of coherence to its entire story. It shows how simplicity can lead to richness, how smoothness can lead to structure, and how a universe that began in a calm, uniform state could naturally evolve into a place filled with stars, planets, and living things. It removes any sense of contradiction between the universe's hot beginning and its low entropy. Heat alone does not determine entropy, arrangement does. In the grand sweep of cosmic history, the early universe was a quiet starting point, simple, smooth, and low in gravitational entropy. As expansion continued and gravity took the lead, the universe moved into more probable states, building complexity as it went. From that low entropy dawn came the vast, beautiful variety of structures seen today. And through it all, entropy rose gently, guiding the universe from its improbable beginning into the richly textured place it has become. It is easy to imagine entropy as a slow fading of structure, a gentle loosening that softens patterns and leaves the world more spread out and more uniform. And in many cases that picture is accurate. Differences smooth out. Warmth drifts. Colours mix. But this can lead to a quiet misunderstanding. The idea that entropy only destroys complexity. In reality, the universe tells a different story. Complexity often flourishes because entropy rises, not in spite of it. Gradients of temperature, pressure, light and energy do not erase structure, they help create it. A simple way to approach this is to imagine any place in the universe where there is a contrast. A warm region next to a cooler one, a bright region beside a darker one, a dense cloud touching thinner surroundings. These differences are not static. They contain potential. They hold stored energy that can be released, redistributed or transformed. Wherever there is a gradient, there is a chance for something interesting to happen. Stars, for example, form because clouds of gas collapse under gravity, driven by tiny differences in density. These clouds were once part of the smooth early universe, but as gravity slowly amplified the small imbalances, the clouds grew denser in some places and thinner in others. Eventually the densest regions collapsed into spheres where pressure rose until nuclear fusion ignited. A star is not a simple object of order. It is a highly structured system existing precisely because the universe began in a low entropy state that allowed gravitational entropy to grow. The star takes dense fuel and spreads its energy across the cosmos. As entropy rises, structure appears. Planets form in a similar way. Around young stars, leftover dust and gas do not lie evenly distributed. Collisions and clumping create larger pieces. These pieces attract more material and grow into planets. The process relies on differences, regions that are slightly more crowded than their surroundings. Entropy increases as energy from collisions spreads outward. The leftover heat warms the forming world. The gradients created by sunlight and internal heat shape its weather, oceans, and geology. Complexity forms in the middle ground, between pure order and pure randomness. Chemistry follows the same quiet pattern. Molecules interact differently at different temperatures. A uniform pool of perfectly mixed material would have few opportunities to create new patterns, but when gradients exist, when one region is warmer, one is cooler, one is oxidizing, one is reducing, molecules can move, react, and arrange themselves into more elaborate forms. Rivers tumbling over rocks, deep-sea vents shimmering with heat, clouds charged with electricity, and sunlight striking the surface of a lake all create conditions where complexity can take root. Life is the clearest example of this principle. A living cell relies on flows of energy, sunlight coming in, chemical bonds breaking and forming, heat drifting outward, waste leaving. Life itself is not a static order. It is a dynamic structure that forms precisely because energy is flowing from a high-quality source, such as sunlight or chemical gradients, into a lower-quality form such as diffuse heat. The cell maintains its low internal entropy by exporting entropy to its surroundings. It is not violating the second law of thermodynamics. It is participating in it in a beautifully coordinated way. This leads to a quietly profound insight. Complexity is often highest when entropy is rising steadily, but not yet finished, when the world is in the middle of smoothing itself out. Too much order leaves little room for patterns to form. Too much randomness leaves no structure to build upon. Complexity thrives between those extremes, in the gentle middle ground where gradients exist, energy flows, and systems reorganize themselves in more intricate ways. Consider a forest. The forest draws energy from the sun, building structured leaves, branches, and roots. But as the forest grows, it releases heat into the air. The low-entropy sunlight becomes high-entropy warmth, radiating outward. The forest is a pattern created in the middle of an entropic process, shaped by the steady flow of energy. Remove the sunlight and the structure fades. Let the energy flow unchecked, and the structure cannot form. Complexity appears when energy flows through a system at just the right pace. Even the weather follows this rule. Clouds, storms, breezes, and currents look complicated because they sit at the edge of balance. The atmosphere receives concentrated sunlight during the day and releases gentle heat at night. This uneven input and output of energy creates movement, turbulence, and beautiful swirling forms. These structures emerge as the atmosphere works to distribute energy more evenly, to raise entropy in a gentle, steady way. The structures are temporary and ever-shifting, but they are real and richly detailed. Cosmic structures behave the same way. Galaxies form as gravity draws matter inward, creating dense regions surrounded by enormous emptiness. Inside those galaxies, stars shine, planets orbit, and dust clouds drift. The galaxies themselves rotate, stir, and slowly change. At every step, energy is moving from concentrated areas to wider spaces. As the entropy rises, the richness of the structure grows. If the universe had begun in a more chaotic state, the complexity of galaxies would never have formed. If it had begun in a perfectly settled state, there would have been no gradients to drive change. Its low entropy beginning allowed the gradual rise of complexity. A gentle metaphor helps bring this idea to life. Picture a calm hillside after a light snowfall. At first, the snow lies in a smooth, nearly featureless blanket. But as the day begins to warm, small differences emerge. A patch melts faster because it catches more sunlight. A drift reshapes itself in a passing breeze. Water trickles in tiny channels. Each change creates more variation, more texture, more complexity. The hillside never becomes chaotic, but it becomes far from uniform. Its patterns grow from a mixture of order and randomness, driven by energy moving across the landscape. Complexity forms as entropy rises. Understanding this resolves a common misconception. Entropy does not forbid structure. It does not erase complexity. Instead, it guides systems away from improbable states of perfect uniformity or perfect rigidity. It encourages them to explore the wider space of possibilities. Complexity is one of the natural ways systems organize themselves, while entropy increases overall. The universe today is full of intricate phenomena, galaxies spinning, ecosystems developing, weather shifting, chemistry evolving, because entropy created the conditions for these structures to arise. Complexity is not a rebellion against entropy. It is one of its most elegant outcomes. Memory is often spoken about as something abstract, like a faint imprint or a quiet echo of experience. But at its foundation, memory is physical. It is built from patterns, structures, and small arrangements of matter inside the brain. When a memory forms, it leaves a trace behind. Connections strengthened, pathways altered, molecules reorganized in a slightly more structured way. And because structure always requires energy to maintain, memory is directly tied to entropy in a calm and deeply natural way. Every memory begins with a kind of ordering. Neurons fire in certain patterns, and those patterns cause some connections to strengthen while others weaken. The brain is not engraving words onto stone or storing images like a photo album. Instead, it is changing its internal landscape ever so slightly to reflect something that has been experienced. Millions of tiny adjustments create a subtle shift from one configuration to another. These shifts require energy, because they move the brain into a state with fewer microscopic possibilities than before. A memory is not a random arrangement. It is a particular pattern preserved within a system that could have been arranged in many other ways. The act of remembering something, therefore, is not passive. It is a quiet investment. The brain uses chemical energy to reinforce pathways, tidy up connections, and maintain the structure that holds the memory in place. Even recalling a memory can strengthen it, nudging the neural circuits so that they remain defined and stable. The system keeps itself slightly more ordered than it would be if those memories were not there. This is why forming and maintaining memories requires energy. It is the energetic cost of keeping certain arrangements intact in a place that is always tending toward greater microscopic variety. Forgetting, on the other hand, increases entropy in the gentlest way. When a memory fades, the structure that once held it becomes looser. The connections weaken. The pattern that once stood out settles back into the larger landscape of possibilities. This does not happen abruptly. It happens through the soft drift of unused pathways, the quiet reshaping that takes place when energy is no longer spent to stabilize them. The loss of memory is an increase in entropy, not because anything dramatic occurs, but because the system moves from a more ordered arrangement into one with far more microscopic freedom. A helpful way to picture this is to imagine a set of footprints in sand. When first made, the prints are crisp, clear and structured. They reflect a particular arrangement of grains, an ordered pattern created by a specific event. But unless someone actively maintains the footprints, the wind and tides gradually soften them. Grain by grain, the prints lose definition, spreading subtly outward until they blend back into the smooth surface. The sand has not lost anything in an absolute sense, but the order that once captured a moment has relaxed. Entropy has quietly increased. Memories follow a similar path unless energy is continually invested to keep their patterns intact. This link between entropy and memory connects directly to the way the mind experiences time. The world only moves forward because entropy rises. Processes unfold. Eggs break, but do not unbreak. Heat spreads, but does not reconcentrate. Scents drift outward, but do not gather themselves back together. For every mundane example, the direction is clear. And the brain has evolved in this world of one-way processes, constructing memories as markers of the moments that have passed. The past is the set of states in which information has been stored. The present is where information is being formed. The future is the region where patterns have not yet been committed to structure. This flow matches the direction in which entropy rises. The experience of time is deeply tied to the accumulation of memories. As the brain records new patterns internally, the universe around it continues moving into more probable states, with each moment leaning gently into the next. Because memory is a form of low entropy, the arrow of time is felt through the creation of new order inside the mind, running against the broader trend of entropy rising. It is as if the brain lays down tiny pockets of structure as the world continually moves toward greater dispersal. This contrast is part of what makes the passage of time feel directional. We remember the earlier, more ordered state and compare it with the present. We do not remember tomorrow because its patterns do not yet exist in a structured form within the brain. Memory builds the sense of before and after. There is a simple and peaceful way to understand this. Imagine walking along a quiet beach. With each step, the sand shifts beneath your feet. The breeze moves gently across the surface, smoothing away the edges of your footprints. The direction you've walked is marked by clearer impressions. The direction ahead is undisturbed. Your footsteps are the record, the structure left behind. The smoothing of the sand behind you is the rise in entropy, and your sense of progress comes from the difference between what has been shaped and what is still untouched. Memory works like those footprints. It gives structure to what has passed. Seeing memory through this perspective removes the confusion between mental experience and physical law. Forming a memory lowers entropy locally, but maintaining that structure requires continuous energy. Erasing a memory allows the brain's patterns to drift into a wider space of possibilities. Time feels like it flows forward, because new patterns form while older ones blend into the background. The world outside becomes more spread out and less structured, while the world inside briefly gathers shape before letting it go. This creates a quiet harmony between entropy and the mind. The brain is always balancing delicately between structure and dispersal. It forms patterns, holds them for a while, and eventually lets many of them go. It is continuously building small islands of order in a world that leans toward openness and possibility. And that is why the feeling of time is so closely connected to memory. The rising entropy of the universe gives time its direction, and the patterns inside the mind give time its meaning. This relationship does not make memory fragile in a sorrowful way. Instead, it makes it natural. The brain participates in the same processes that guide stars, oceans, storms, and galaxies. It uses energy to create structure. It releases structure back into the wider flow. It records, it adjusts, it forgets, and it remembers again. Memory is not separate from the physical universe. It is one of the ways the universe expresses itself through structure. In this calm view, entropy and memory are not opposites. They are partners in shaping experience, each doing what they naturally do. Entropy softens and spreads. Memory gathers and defines. Together, they create the quiet sense of a world unfolding in one direction, step by gentle step. Far in the future, long after the last familiar lights have faded, the universe will continue drifting toward a state of deep quiet. This future is not sharp or frightening. It is not even sudden. It is a gentle, almost serene continuation of the same process happening everywhere right now. The gradual spreading of energy, the soft leveling of differences, the patient rise of entropy. To picture this future clearly, it helps to imagine the universe letting go of its contrasts one by one, smoothing itself into an expansive calm. The journey begins with the stars. Every star is a pocket of concentrated energy, shining because it is steadily dispersing that concentration into space. Over millions of years, a star uses its internal fuel to emit light and heat, releasing energy that travels outward across vast distances. As that energy spreads, entropy rises. Stars are temporary structures, beautifully intricate but dependent on gradients that slowly fade. When a star exhausts its fuel, it cools, dims, and eventually settles into a quieter form. Some become white dwarfs that slowly radiate away their residual warmth. Some collapse into neutron stars or black holes. Each step is a movement toward a more even sharing of energy. Galaxies, too, take part in this slow unwinding. The expansion of the universe pulls galaxies apart from one another, stretching space itself. Over extremely long time scales, this expansion grows so large that galaxies drift out of view, their light redshifting into wavelengths too long to detect. In the distant future, an observer inside any given galaxy would see fewer and fewer neighbours until the surrounding sky becomes almost empty. This emptiness is not a sign of loss. It is simply energy stretching itself thinner, becoming more evenly spread across an expanding cosmos. As the expansion continues, the stars within those galaxies fade one by one. New stars form less often. The remaining ones grow old. The chemical energy stored inside planets dissipates. Gas clouds thin out. Regions that were once warm and bright become cooler and dimmer. The contrasts that once shaped structure slowly relax. The process is gentle, like a warm ember softening into a quiet glow and then into comfortable darkness. When this spreading of energy reaches an extreme, the universe approaches what scientists call heat death. Despite its name, heat death is not a violent ending. It is the natural outcome of entropy reaching its maximum possible value. In such a state, energy is so evenly distributed that no usable gradients remain. There are no warm places and cool places, no bright pockets and dark pockets, no regions of high density or low density that could drive new structure. Everything is smooth, everything is settled. Heat death does not refer to the universe becoming cold in the everyday sense, although it will be very cold. Instead, it describes a state where no more work can be done because all contrasts have faded. Energy is still present, but it is too evenly spread to create change. The arrow of time, which relies on entropy rising, becomes subtle and faint because entropy can rise no further. The universe is not erased, it simply becomes still. A helpful way to imagine this is through the image of a lake at night. Early in the evening, the surface might be rippled by fish moving beneath it, by breezes passing across it, or by rain falling. But as the night deepens, the disturbances fade, the water settles, the ripples smooth out. By midnight, the lake may appear perfectly calm, its surface reflecting the sky above. Heat death is like that calm. The lake still exists. The water still moves at a microscopic level. But on large scales, everything has relaxed into a peaceful uniformity. In the same way, the future universe remains full of activity on tiny scales. Particles still vibrate, light still moves, space still expands. But the large contrast that once powered stars, planets, chemistry, and life no longer exist. The universe becomes a place where everything is spread thinly and evenly, and where change happens only in the smallest, most subtle ways. Black holes persist for a time, silently shaping their surroundings, but even they are not permanent. Over staggering expanses of time, black holes emit faint radiation and gradually shrink. A black hole that once held enormous entropy slowly releases its energy in delicate whispers into the surrounding space. Eventually, even these last structures fade, leaving behind a universe filled with diffuse, thinly spread radiation. This stage is surprisingly tranquil. There is no collapse, no explosion, no dramatic ending. Instead, it is a settling, a vast cosmic exhale. The universe has spent its long history spreading energy into more possible arrangements. It has built stars, galaxies, planets, storms, forests, oceans, and countless patterns along the way. And after all those patterns have come and gone, the universe relaxes into the simplest, broadest state available to it. Maximum entropy does not mean nothingness. It means completeness. It means the universe has explored its full space of possibilities and reached the smoothest, most evenly distributed form it can take. This smoothness is not oppressive. It is quiet, calm, open. If the early universe was a taut bowstring filled with potential, the far future universe is the soft release after the arrow has flown. There is something gently poetic in this long arc. The universe begins in a low entropy, highly ordered state, smooth, bright, dense. It grows more complex as entropy rises, forming galaxies, stars, and life. It reaches moments of extraordinary structure and richness. Then, slowly, the energy spreads. The contrasts soften. The structures unwind. And eventually, everything drifts into a tranquil stillness where there is nowhere left for entropy to rise. Seeing the far future in this light removes the need for fear. Heat death is not a cold doom, but a quiet phase in a very long story. The universe becomes spacious and even, a resting place shaped not by endings, but by the natural spreading of energy. It is the ultimate expression of entropy, not as destruction, but as the soft smoothing out that has always guided the cosmos. In this distant future there are no bright lights or sharp differences, but there is a kind of peace, a stillness, a vast openness where everything has settled into its most relaxed form. And just as the early universe held the seeds of all future complexity, this future universe holds the calm completeness of everything that came before, spread softly across the widest space imaginable. The universe might appear to be a contest between order and disorder, with neat structures on one side and spreading randomness on the other. But when looked at gently, the relationship is far more harmonious. Order arises in small places not because the universe rebels against entropy, but because creating local structure is one of the natural ways entropy increases overall. Stars, storms, living organisms, crystals growing in cold caves, these are all pockets where order forms, and yet each one depends on energy flowing through it, and that flow always releases more entropy into the surroundings than the order reduces within the pocket itself. A clear way to see this is by returning to the image of a star. A star is a beautifully organized object, a sphere of gas held together by gravity, burning steadily, producing heat and light in enormous quantities. Yet a star is not a contradiction of the second law of thermodynamics. It is one of its greatest expressions. A star reduces entropy inside its core by fusing hydrogen into helium and creating structure, but it does so by releasing far greater amounts of energy outward. That outward flow spreads through space and increases entropy on a massive scale. The star's internal order is a tiny island, and the light it emits is the widening sea of entropy surrounding it. Life follows this same pattern. A living cell is a highly ordered system. Molecules inside the cell are arranged with astonishing structure and precision. Proteins fold into exact shapes. Membranes divide compartments. Energy flows through pathways that would collapse without careful control. But none of this order appears from nowhere. The cell must continuously take in energy, sunlight for plants, chemical energy from food for animals, and convert it into forms that maintain its internal structure. While doing so, it releases heat and waste products. These releases increase entropy outside the cell, even as order grows within it. A simple way to picture this is with a candle. The flame is a structured shape with a clear boundary. It seems orderly, almost delicate. Yet the flame exists only because the candle's wax is burning, turning dense chemical energy into heat and light. The flame is the visible part of the process. The release of heat into the surrounding air is the entropy being created. Without that wider increase, the flame would vanish. Its order is supported by the dispersal around it. Storms also create structure for as long as they exist. A storm is not random. It is organized in swirling patterns, rising columns, and rhythmic movements. It does not form in calm air. It forms when warm, humid air meets cooler, drier air, a gradient waiting to be smoothed. The storm is the mechanism by which the atmosphere evens out the imbalance. The dramatic winds and cloud formations appear orderly, but the purpose is simply to spread energy. The storm's beauty is the visible part of entropy at work, releasing heat and moisture until the differences that powered it disappear. Crystals offer an even quieter example. When water freezes, the molecules arrange themselves into a repeating lattice. The ice that forms is low entropy, because the molecules are arranged in a clear repeating structure rather than in a chaotic liquid. But freezing releases heat into the surrounding environment, increasing entropy outside the forming crystal. The crystal grows only because the surrounding universe absorbs the heat that must be given up. Order appears locally, and entropy rises globally. This balance, order in small places, entropy rising everywhere else, exists in countless natural processes. A plant leaf forming its chlorophyll-based structures is lowering its entropy, but the sunlight that powers the process warms the air and increases entropy around it. A snowflake forming its symmetrical branches is lowering entropy in the ice lattice, but the freezing process releases heat into the surrounding cloud. A seed sprouting into a sapling builds layer after layer of precise organized tissue, but the metabolic processes that make this possible release far more heat and randomness into the environment. In each case, energy flows from a concentrated source toward a wider space. That flow creates opportunities for order to form temporarily, because systems follow gradients as they relax toward a more probable state. The order is not permanent. It persists only while the energy flow continues. When the flame dies, when the seedling lacks sunlight, when the storm exhausts its temperature difference, the order relaxes and entropy continues its quiet rise. A gentle analogy makes this idea feel intuitive. Imagine a cold room with a single glowing radiator on one side. The radiator releases heat into the room, and the air flows around it in graceful patterns, rising currents, circulating loops, subtle swirls. These flows are orderly because they exist in response to a difference. Warm air near the radiator, cooler air farther away. The patterns allow the heat to spread more effectively. As the room warms and reaches equilibrium, the patterns fade. The flow becomes quiet. Order emerges to speed the rise of entropy, and then gently disappears. In the same way, every structure in nature can be seen as a temporary pattern that helps energy spread. The pattern may be delicate or dramatic. It may last a fraction of a second or billions of years, but in each case, energy flows through it, and the flow increases entropy in the wider environment. These patterns are not exceptions to the second law. They are part of how the second law unfolds. This gives a peaceful perspective on the world's complexity. Order is not something the universe reluctantly allows. It is something the universe produces as it moves toward equilibrium. The pockets of order, living beings, storms, stars, crystals, are like eddies in a river. Each whirlpool forms because water is flowing from a higher point to a lower one. The whirlpool is a structure created by the flow, not a denial of it. And as long as the river runs, such patterns appear and fade. This view reveals an elegant balance. Local order requires energy. That energy flow always generates more entropy than the order reduces, and the global increase in entropy creates the gradients that allow new local order to arise. The entire cycle is harmonious, not conflicting. The spreading of energy makes structure possible. Structure helps energy spread more effectively, and the universe moves slowly and calmly along these pathways. Seen through this lens, order and entropy do not live on opposite sides of nature. They are intertwined, each shaping the other. The universe holds countless small, intricate patterns, stars burning, cells dividing, snowflakes forming, because these patterns sit in the gentle currents that carry energy outward. The background trend is always toward greater entropy, but along the way, the universe creates small places where order briefly flourishes, supported by the wider increase happening everywhere else. This relationship is not a struggle, it is a natural rhythm. Pockets of order blossoming in a world that prefers spreading, each one a temporary expression of the flow of energy across the cosmos. In a quiet moment, it is worth remembering that your life unfolds within a universe shaped by the slow, steady rise of entropy. Every breath you take, every heartbeat, every thought moving gently through your mind depends on energy, flowing from a more concentrated form into a more dispersed one. The warmth in your body, the activity of your cells, the patterns of memory and experience that make you who you are, all of these processes rely on the same spreading of energy that guides stars, oceans, storms, and galaxies. Entropy does not sit far away. It is present in every moment of living. Your body stays alive because energy enters, moves through you, and eventually leaves in a more spread out form. Food breaks down into simpler pieces, releasing heat. Muscles contract and relax, releasing more heat. Neurons fire and reset, turning chemical energy into electrical signals. At each step, you build small pockets of order, memories, thoughts, motions, repairs, while the world around you becomes slightly less ordered. This is the same pattern seen everywhere in nature. A local rise in structure supported by a larger rise in entropy elsewhere. Even something as quiet as sleep follows this pattern. As you rest, your metabolism slows, but it never truly stops. Your cells continue their gentle work, maintaining structure, clearing waste, and preparing you for the day ahead. Tiny currents of energy keep your body warm. These currents flow because the world outside is cooler than you are. Without that gradient, the warmth could not leave your body, and the delicate internal processes that keep you alive could not continue. Your personal experience rests on this background flow of energy from warmer to cooler, from concentrated to dispersed. Stepping farther back, your entire existence depends on a chain of unlikely events sculpted by entropy. The star that warms your world formed because a cloud of gas collapsed under gravity, raising entropy by releasing heat and light into space. The planet you live on formed from leftover material circling that young star, slowly clumping together in a process that increased entropy through countless collisions. The chemistry that led to life emerged in places where gradients of heat, pressure, or sunlight created opportunities for molecules to arrange themselves in useful ways. Each step was part of a long, natural movement toward more probable states. Your ancestry stretches back through this chain. Your parents, grandparents, and every generation before them relied on energy flowing through ecosystems, weather patterns, plants, oceans, and food webs. Life on Earth has always needed sunlight as its primary source. That sunlight is the outward flow of entropy from the nuclear reactions inside the sun. Every leaf, every blade of grass, every meal ever eaten depended on those flows. The complexity of life formed in the middle of these gradients, just as stars and storms and chemical reactions do. Even your thoughts reflect this cosmic pattern. A thought forms when neurons fire in a coordinated way, creating a pattern of activity within the brain. Maintaining that pattern requires a flow of energy, and that flow produces heat that escapes into the surrounding air. A moment of reflection, a quiet memory, or a gentle feeling all involve a local increase in order inside your mind, supported by a larger release of entropy outside it. The universe becomes slightly more spread out every time you think, breathe, move, or feel. There's something comforting in this perspective. It shows that you are not separate from the rest of the cosmos. You participate in the same processes that guide the evolution of stars and the drifting of galaxies. Your life is woven into the fabric of entropy's rise, not as an accident, but as one of the natural patterns that emerges along the way. If the universe had not begun in such a smooth, low-entropy state, the gradients needed for stars, planets, chemistry, and life might never have existed. Your existence is one of the outcomes of the universe exploring its possibilities. This does not make life fragile in a worrying sense. Instead, it highlights how deeply connected your experience is to the wider world. You rely on sunlight filtered through the atmosphere, food grown in soil warmed by that sunlight, water lifted into clouds and returned as rain, air mixed and carried by winds. Each of these processes moves energy from a more concentrated place to a more dispersed one. Entropy rises in each step, and through these rises, your life is supported. You're also shaped by entropy in another sense. Time feels like it moves forward because entropy increases. The future is the region where entropy has not yet risen. The past is the region where it already has. Memories mark the places where energy once flowed through your mind, creating traces of what happened. The moments ahead are open because their patterns have not yet formed. This gives life a sense of direction, not from urgency, but from the way the universe itself gently unfolds. Seeing your life in this panoramic way can bring a kind of calm perspective. The same processes that drive the expansion of the universe also help carry you through your days. The same logic that shapes galaxies also shapes the warmth in your hands. The rise of entropy is the quiet background that makes your experiences possible, from the smallest heartbeat to the largest thought. You're a temporary, beautiful structure through which the universe lets energy flow. And although entropy ensures that no structure lasts forever, it also ensures that new structures can arise. Stars forming from clouds, life growing from chemistry, thoughts forming from electrical patterns. You are part of that ongoing story, present because the universe has been rising gently toward more probable states for as long as it has existed. In this sense, the idea of entropy becomes something soft and personal. It is the quiet companion of every moment, the gentle backdrop that allows your life to unfold. It makes warmth possible. It gives time direction. It allows structure to form in your mind and body. And as you settle toward rest, you can feel its presence not as something distant or abstract, but as something woven into your existence, carrying you calmly into the next moment and the next. In the quiet of this final moment, the whole journey settles into something simple and reassuring. Entropy, which can sound so vast and technical, is really just the universe's gentle tendency to spread things out, soften differences and balance contrasts. It is the background rhythm behind warm hands cooling in the air, behind a cup of tea settling to room temperature, behind weather drifting across oceans, and behind stars sending their light outward into the dark. Everything moves from concentrated to shared, from sharp to smooth, from unlikely to more probable. And through that slow, patient drift, the cosmos forms patterns, dissolves them, and forms them again. We began in the early uniform universe, where everything was smooth and bright and full of potential. From that low entropy beginning came stars, galaxies, planets, chemistry, and eventually life. Along the way, energy flowed in all directions, creating small pockets of order. Living cells, beating hearts, blooming ecosystems, drifting clouds, each supported by a larger release of entropy around them. Entropy guided the growth of complexity, not by breaking patterns, but by opening the pathways through which new ones could appear. We followed that thread through storms and oceans, through the light of stars and the darkness of black holes, through memories forming inside the mind and the quiet future of the expanding universe. And underneath every chapter was the same idea. Energy spreads, differences soften, and the world becomes more open, more even, and more spacious over time. This is not something to fear. It is the reason anything happens at all. Entropy is the quiet companion of every moment. It gives time a direction. It allows warmth to flow, life to grow, storms to swirl, and galaxies to shine. And here, at the end of this journey, it reaches back to connect the vastness of the universe with your own experience. Every breath, every thought, every small pattern your life creates is part of this same gentle drift toward balance. You are living within the universe's patient smoothing out, shaped by the same processes that guide stars and fields of drifting starlight. If this slow exploration helped to bring a little calm into your evening, or gave you something peaceful to drift off with, please do consider giving the video a like, leaving a comment, or subscribing if you haven't already. And if you are already subscribed, thank you. It genuinely helps this little corner of science continue to grow. If you have a moment, tapping the notification bell means you won't miss the next gentle journey. For now, though, you can let the ideas soften and settle, just like everything else in the universe eventually does. Let the thoughts drift outward. Let the last bits of tension unwind, and allow yourself to rest. The universe will continue its quiet spreading, its smoothing out, its gradual glow into the future. And you, right now, can simply breathe in the calm of this moment and ease gently into sleep.